Today we will wrap up chapter 5 by talking about the termination detection. Okay. Um, so as we all know, for a payroll program, right, we have to determine when the program should terminate, because if any of the process keep running, then the whole program will not stop, right? All the process need to determine when it can be finished at certain point, right? And the earlier the better, right? Like homework one, right? In for the so for the sorting algorithm, right? The odd even sort, you actually don't need to iterate through n iterations, because your number maybe gets sorted at earlier iteration, maybe even the first iteration. So if you can determine earlier, that means you can complete the computation earlier. Then you can shorten your execution time. How to determine a termination condition is actually quite important in payroll program, right? Not only you can avoid error or those problems, but also can reduce the execution time. Okay. However, to determine the termination condition, actually it's not as simple as you might think in payroll program. The reason is that I think in the past, your termination condition is very likely just make the decision depending on the local information, right? For example, like the load balancing, like this one, right? Like the dynamic load balancing solution as shown over here. We said the master, right, can determine when the program should be finished by checking the work pool, right? If the work pool is empty, then he knows the program can complete, right? But however, that is because the master has a global information, right? He control everything, so he can determine when the program should terminate it by himself. Okay, but in the fully distributed payroll algorithm, like the one we introduced at the end of the last lecture for shortest path, as shown over here, right? You can see in this case, we don't have a master. We have all those processes or workers they have peer-to-peer relationship. So each of them holds a local working pool, right? And even more than that, the task, right, the computing task actually could be generated at the wrong time through the message. Okay, so the termination condition as shown over here, actually for payroll program, there are two requirements if the program can really terminate. The first one is you do need to check the local information, and you have to check the local information for every single processes to make sure they reach their termination condition, such as their local work pool is empty, right? But besides that, more importantly, most people probably overlook this condition, is that there cannot be any message in transition when you determine that condition. Why is that? The reason is like this example, right? You could imagine maybe at runtime, right? At certain point, maybe all the processes, their work pool are already empty. Okay, but actually there is a new task get generated by a message sent by P to C, right? But sending the message takes time. So there is a time difference, right? When you check all the condition, local condition, the work pool is empty, doesn't mean it will stay empty. Because if for the next second, maybe the message arrive, then it will generate a new task. Then you should keep running, right? You cannot terminate too early. right? Um, so for parallel program, actually not only the local pool needs to be empty, you also need to ensure there's no more message, especially for the program that a computing task can be generated by messages. Okay. Of course, if you're in your application, if the message cannot generate the new task, then maybe it become easier. However, sometimes we still need to wait, right? Because if we need to terminate the whole program, that means we need to make sure any message in transition has to be received. So you still have to wait, right? Wait until all the messages are received, then you can terminate. Okay. So even for the centralized work pool, right? We introduced the pseudocode before. If you can recall, at that time we also have a variable named count, right? Which is try to uh, keep track of how many messages are sending or how many clients are still active, right? So the purpose of that count is to make sure if count equal to 0, and then we can make sure there's no more message is sending between the slave and the worker. So only until then we can terminate the program. Okay. So that's another example, right? Not only that we need to make sure the working pool is empty, but also there's no more message in transition. Okay. All right. And the first condition is simple because it's a local condition, right? So you can simply write some code and check the local information to see if the local termination condition is reached. But the second condition is hard, right? How can you know there's no more message in transition? Okay. Again, for centralized, the example of centralized load balancing, it might be easier because you expect to receive the message. So you know when the message should still in transition because you have to wait until you receive the message you expecting, right? However, right, in this example, you can see that this is a completely fully distributed implementation. So for any given process, it has absolutely no idea whether there will be a new message uh, generated and send it to him, right? Because everything is decided at wrong time. So you don't know when and how many messages will you receive. Okay. So it's always the big problem for not only the payroll algorithm, but also for the distributed systems. Yeah, because the message will have the latency, you have network latency. So it's actually hard to determine whether you have a message arrive or not. Okay. All right. So it's not a simple problem in short. Okay. Um, so how can you solve it? Okay. One of the solution called the single pass ring. This is probably what you could imagine. It's a naive solution. However, it only can satisfy the first condition uh, by checking the local termination condition. It cannot solve the second condition about the message in transition messages. Okay. So, but let's first look at the solution of single pass, and then we will introduce the dual pass ring algorithm, which can address both conditions. Okay. So, what is a single pass ring termination algorithm? The idea is pretty simple, right? Because the the termination condition, right, can only be reached if every local condition is satisfied. So we use a token, right, to pass around every single processes to make sure all the conditions are satisfied. Okay. So the token start from some master or some root, right, such as P0. And P0 will hold the token until he reach the local termination condition. such as the workpool is empty. Okay, and when his local termination condition is reached, he will pass the token to the next process, and the next process will do the same thing, holding the tokens until his local condition is also reached. Okay, so you can imagine, right? If we do this so on and so forth, then supposedly when P0 receive the token again, that means every processes has reached their termination condition. Okay, so since everyone reached their local termination condition, then that means the whole program can finished, right? So the P0 will then send out a signal, right? You can broadcast, or again, you can pass by ring to notify every other processes to just uh, finish or complete their execution. Okay. This algorithm is pretty simple, pretty straightforward, and it will be correct if the process cannot be reactivate. Okay. So what is mean by reactivate? Reactivate means that once a process reach a termination state, it cannot reactivate into a running state. Okay. So this algorithm only work under that constraint. Okay? And obviously, it will not address the second problem, right? The second condition, which says that a process, right, can be reactivated by a message. Because if a message generate a new task, then it will reactivate the process that received the message. Okay, all right. Um, that's why we say single pass ring can only satisfy the first condition, and it has a requirement that any process cannot be reactivated if once it reached the termination state. Okay. All right. So what is a dual pass ring termination algorithm? Okay. This is way more complicated, or especially if you implement it, you will know how hard it is. Okay, not just to understand, but in order to correctly implement it, it's very tricky because it involves some synchronization issue. We used to have it as a homework, but we find that it's so hard to verify the correctness. So we didn't include that in our homework anymore. But it's actually a very interesting problem. And if you really implement it, you will find out how hard it is to implement it and verify it. Okay. But anyway, the concept of this algorithm is that it will pass the token twice before it makes sure it reach a global termination condition. Okay, and why it needs a two pass? Because in the first pass is similar to before. Okay, same as before. Every process, the token will start from say P0 or the master, and then pass on one by one. If the process reach its termination condition, local termination condition, then it will pass the token. Otherwise, it will just hold the token. Okay, wait until it is terminated. Okay, all right. But that's for the first pass. So we use the color to indicate whether this token is valid or not. Okay, so as you can see at the beginning, the token is valid token, so it's colored by white. Okay, however, a process can invalidate, okay, make the token become invalid by color the token to the black color. Okay, so when a token will be invalidated, it will a process will invalidate the token if the process try to send a message in the backward direction before he received the token. Okay, so what's the reason behind it? The reason is because imagine, right? Um, if some process send the message backward, right? It is possible, right? There is a chance the receiver, like PJ over here, already passed the token forward. So that means PJ already declared it is terminated. But if a backward message happened, then PJ could be reactivated. Okay. So whenever there's a backward message, it is possible to have a reactivation on some processes. Okay. So since there's a possibility, so in order to make sure there's no reactivation occurred at all. So to be safe, when there's a backward message happen, then the process will color itself into black color and wait until he received the token. And if he received the token, he cannot trust the token because he doesn't know the token has passed PJ or not, right? Before he send the backward message. So that's why he will, because he doesn't trust the token, so he will mark himself as a black color and wait until the token arrives. And when the token arrives, he will color the token into black color as well. Okay. And then what happened is that this token will simply just keep passing on to P0, and P0 will know this run is failed. Okay. So P0 will color the token back to white and restart the ring passing steps again. Okay. You will keep doing this until P0 can actually receive a token that is in white color. Okay. So the idea is that right, the single pass ring is correct if there is no reactivation. So the dual ring try to solve that by determining all the determine what's the possible action that can trigger reactivation. Okay, and he tried to avoid the reactivation occurred, right, for a valid ring pass procedure. Okay, so as you can see, if P0 actually receive a token in white, that means during the whole process, right, when we pass this token back in this whole time, there's no backward message happen. Since there's no backward message happen, that proves there's no reactivation could happen. So if there's no reactivation happen, then even a single pass can correctly identify a global termination condition. Okay, so that's the idea. Okay. By the way, if you wonder, if you wonder why we don't invalidate the token for forward message, that is because, right, for example, for PI, right, um, if PI is since PI hasn't received the token yet, so whether he send a forward message or not become irrelevant, because if it's a forward message, that means whatever the receiver is, he also doesn't receive the token yet. So it will not invalidate the token, right? He will not reactivate. Whether it activate or not, it doesn't matter because that receiver hasn't report his termination condition yet. Okay. So forward doesn't matter, but backward matter because backward may trigger a process that already report it is terminated. Okay, so that violate the assumption, so we have to invalidate the token. Okay, all right. So this is what we call the dual pass ring termination algorithm. Okay, so it's possible. It's not dual pass. It's an infinite number of pass until you have a valid a valid run, a valid token receive. Okay. All right. So we have some animation for you to help you, to understand actually what happens step by step. So like the first step, as we said, P0 will at the beginning every processes is in white and the token is also in white. Okay, and start passing the token as long as he reached the termination condition. the local termination condition. Okay. However, a process, as I said, it will color itself to black, right? If he hasn't received the token and he tried to send the message backward, right? We can use the ID, the process ID, to identify whether it's a backward message or forward message, right? And after he color his cells to black, he might wait for a while, right, before he receive the token. But once he received the token, he will color the token to black and send it to the next process. And once the token is in black, it doesn't matter anymore. So all the downstream process will just simply keep forwarding the token to until he reach P0. And unfortunately, this run is meaningless. So P0 will restart the step one again. Okay. All right. So as we said, the only possibility that P0 can receive a white token is everyone reach local termination condition, and no reactivation occur in the whole process. So that meet both requirement we mentioned. Okay. Right. So this is a complete end-to-end step-by-step illustration of the algorithm. Okay, so you can trace it by yourself and see actually what happened. Okay, as you can see over here, the reactivation happened because P1 already sent the token to P2. Then P3. After that, P3 send a message to P1. So this is a reactivation. So we have to make sure P0 is notified that a reactivation is occurred, and it will be notified by P3 because P3, by the worst case, right, he will notify that to P0. Okay, we say it's a worst case because sometimes a backward message may not trigger a reactivation, right? For example, if P3 send it to P2 before P2 receive the token, then this backward message will not generate reactivation. But we don't know for sure. So we consider the worst case and invalidate the token. So this is really time consuming to correctly determine the right condition. Okay. Yeah. So as you can see, it's actually not a very, very trivial problem, and it's hard to implement, and it will cost a lot of computation and communication. So unless so sometimes that's why people may figure out some centralized or approximation solution, so you can determine the global condition in a more efficient way. Okay. All right. So that's it for chapter 5. So we introduced quite a few payroll algorithms and talking about the load balancing and the termination problem. Okay, those are the important issue that you should consider for payroll algorithm, especially if it's a fully distributed payroll algorithm. Okay. All right. So we will move on to the next lecture. Okay. Does anyone